this would be xnv, xn plus 1v, right? And then this one would be maybe xn minus 1v plus 1, etc., right? So this is clear, right? Yep. And the point is that the dynamics is local in the sense that this point depends on the previous time step only on its neighbors, right? So maybe let's write it out in sort of form. So basically, if you want to write this out as an equation rather than a density, what you would write in some sense is our model is that xnv is some function f of xn minus 1 of w for w basically in the neighborhood of w are the neighbors of v, which includes v. So nv is neighbors of v in whatever graph, including v. Right? V itself in whatever graphical structure you put on the set v. So, you know, so if this is z2, then okay, it's clear, right? Okay. So it's a function, so maybe I should write, let me write it a little bit more cleanly. So basically, each coordinate is a function of the neighborhood of that point in the previous time step, right? Let's write it like this, and some noise. And the noises are independent, right? So this is basically the model. It's a whole bunch of, if you want, it's a whole bunch of models, one on each coordinate, that are coupled locally to each other. Does it make sense? Yeah. Okay. And the observations are really going to be local, right? So these are going to be some function of xnv and some other independent noise. So this is the sort of model. I don't really need this, I don't want this formulation of the model in terms of these functions. It's just to make it clear what is actually going on in this story, right? So the observations are pointing out like that. Right? This is y and t, etc. Okay, so what we really care about is not this formulation, but the densities, right? So we want the transition densities of this model. So if you look, if the transition density, so now we're working in a finite set, right? So let's take V finite. So we can really work in a finite set now. Right? So the transition density, so what is it? It says that Pxn is in A given xn minus 1 equals x. So this is integral A Px x prime dx prime, right? But the point of this model is that I can write, so little p is the transition density of this Markov chain. But the point of this model is that I can write P of xy as a product of the local transition densities. Right? I shouldn't use y, let's use z. All right, so P little v is just the transition density, right? It's the conditional distribution of x and v given xn minus 1 and v, right? Right? And it's a product because the noises are independent, and so when I condition on what happened in the previous time, so the noise is independent. So again, you can generalize this, you can use dependent. I mean, but we're trying to capture the basics of the phenomenon. And similarly, the observations are also, right? So the observation density g of xy, which I already defined last time, is also a product of the local observation densities. And these only depend on xv, not on the neighbors of v, right? So the model is defined in terms of these local, right? In the normal filtering model, you just define one transition density and one observation density. But here the model is defined in terms of this family of local transition densities and these local observation densities. Right? So I should also point out that, by the way, that before I said observations could be attached to a subset W of the states, right? And here I have them in all. But actually it's the same thing, because if I want to turn off the observations on some of them, I just choose those GVs to be 1, right? And then those observations are uninformative, right? So everything is captured in this. Okay. All right, so we have to talk about, so here's the idea. So these are high dimensional distributions, right? That each time it's a random field. So one thing you might try to do, so one naive thing, so forget about localization or anything. One naive thing you might try to do to run a particle filter, so we're going to use something like a Gibbs sampler to sample in space in each step, right? So you could already try to do that to approximate the filter. So a naive Gibbs sampler particle filter would be something where we try to pi n would use a Gibbs sampler. So we sample here, let's say, using the Gibbs sampler. To sample from so without the sampling, this is the ordinary filter. And to have the usual bootstrap particle filter, I stuck the sampling operator inside here. That's what gives you the algorithm that you know, everybody has been using on their slides, right? Now, the ideal thing to put is to sample here, but this is much harder because you already have to sample from a weighted density. So you already have a problem there. But that's why now we could, rather than sampling independently, we could use the Gibbs sampler to try to sample from this weighted density. Or Metropolis, or whatever it is you like to, whatever Monte Carlo it is. And so the point I'm going to try to make is if you try to do this in high dimension, you're going to run into the curse of dimensionality again, okay? But let's try to do it and see what happens, right? So a Gibbs sampler, does everybody know what a Gibbs sampler is? So a Gibbs sampler is a very simple idea. What is a Gibbs sampler? So a Gibbs sample, let's say I want to sample from a distribution mu on, let's say, some high dimensional space. It doesn't have to be R, it can be anything. We want to sample from the distribution on a high dimensional space, right? So one way to do it is as follows. So rather than sampling directly from mu, which can be very hard, it might be easy to sample from the conditional distribution of one coordinate given all the other coordinates, right? So the idea is what you do is you pick a coordinate, v, in 1 to d, right? And then, so you pick some coordinates, and now in each step, we're just going to update one of the coordinates of the distribution, right? And then what we do is sample, so, okay, it's a Markov chain Monte Carlo algorithm. So we start with x tilde 0 initialized to something, right? And then in each step, so you repeat, so you pick a coordinate, and then what you do is you keep all of the other coordinates frozen, right? And you just update the coordinate that you picked, right? So what you do is set x tilde I, x tilde n, for all the sites except for, let's call it I, is x tilde n minus 1, I for all I except for v, right? So in each step, you keep all of the coordinates the same except the coordinate that you've chosen to update, and you sample x tilde nv from the conditional distribution of xn of xv, of the vth coordinate, given all the other coordinates, or d. So the idea is in each step you pick a coordinate, you imagine that all the other coordinates are frozen, right? And you just sample that one coordinate conditioned on that all the other coordinates take whatever values you have before, right? And you keep doing this over and over again. So in each step you pick a vertex, and there are many ways to do this. You could pick one randomly, but you could also just sort of cycle through them, you know. It doesn't really matter how you do it, as long as you hit all of them infinitely many times, right? So you do this over and over again. You pick a vertex, and you just update that coordinate given the conditional distribution, right? And if you do this infinitely often, then this is a Markov chain. You can check very easily that mu is actually an invariant measure. I mean, that's more or less obvious, right? Because if I hit mu with the conditional distribution, that's just the chain rule for the relative, that's just the, sorry, it's just the Tower property of the conditional distribution, right? So it's clear that mu is an invariant measure for this Markov chain, and under some minimal conditions, this Markov chain will converge to the invariant measure, right? So, So the Gibbs sampler is a way of sampling a high-dimensional distribution one coordinate at a time, right? And you would want to do this exactly when sampling from U might be hard, but sampling one coordinate might be easy, right? So that's a situation in which you want to do something like this. Is this clear more? And this is a very classical approach. I mean, this is something that shows up very naturally in statistical mechanics, but then I'd have to define Gibbs measure. I beg your pardon? Well, at each time, the state, the new state is a function of the old state and some independent randomness, right? Say this again? By construction, yes, it's a Markov chain, right? So this is a Markov chain Monte Carlo method, right? Yeah. So, right. But basically for me, I don't even care too much about this. For me, the Gibbs sampler is a tool to construct the whole measure from its conditional distributions. Right? So let's try to do it here. So here we have this measure CNP, which is this weighted measure. It's sort of a nasty measure. We don't know how to compute this thing. So let's try to sample from it using a Gibbs sampler. So to use a Gibbs sampler, so what we would have to do is we would have to take this measure. Let's give this thing a name. Let's call this pi hat n, right? So this is right before we sample, right? So this is, we just took the first one and we propagated it forward, right? And the idea is we need to compute basically the conditional distribution of each of the coordinates given all the other coordinates, right? Because in order to use a Gibbs sampler to sample from this distribution, we're just going to go through each coordinate one at a time or randomly, however you want. And each time we're just going to update the coordinate based on this conditional distribution of just that coordinate based on the rest, right? But these are the conditional distributions under the push forward measure from the filter in the previous time step. Right? So how does it work? Well, we can just compute this. It's easy to compute this object. So what is this? So if you write it like this, by the base formula, this is just the integral over A. So we start, okay, what do? We start in the previous time step, right? Dx prime. Then we get the transition density, right? And then we get the observation density. And then we have to normalize. Sorry, did I do it correctly? Indicator A of x. Sorry, I didn't do it right. So this is indicator A not of x, but of xv. Let's write it out carefully. So I start in the previous time step. I simulate one step forward. And now I have the likelihood of the observations, but I only integrate against xv, right? Because I want a condition on all the other coordinates, right? So if I looked at it like this,
you're not conditioning on the observations.
I'm also conditioning on the observations because of Cn, right? So I'm conditioning on the observation because of Cn, but now I want to condition also on the x's outside, right? So what I'm going to do is I'm just going to neglect to integrate over the x's that are not v, right? And now I normalize this, right? X, dx prime yn. And now I also have dx, right? So now it looks, okay, what is nice about this? You see I'm only integrating against xv. If you look at the density of the observations, this is a product measure. xv only shows up in the v point, right? So here, the rest of them, I'm going to pull them out of the integral, and they're going to cancel in the numerator and the denominator, right? So actually, in this case, in this particular case, I can just replace this g with a gv. G prime v. because I'm only integrating against xv, so all of the observation densities except for xv drop out, right? So when I compute the conditional distribution only of one vertex, I only need the observation at that vertex to sample from this, right? So in that sense, it almost seems like I've already beat the curse of dimensionality because I've dropped out all of the observations except for one, right? And it was the dimension of the observations that was the problem, right? But it's not true because now I have a different problem. Because now I have all these p's in these weights. And the p itself is a product of v of these guys. So if I try to do this, I drop out the observations, but now I get a product of dimension p's. So for example, if this, remember, this thing are n samples, right? So in order to sample from this distribution, what I'd have to do is for each particle, I'd have to actually compute the transition likelihood, which is a full product of v transition kernels, right? Multiply just by one observation weight and then renormalize with those weights. But you see, the weights are still going to be a product of v elements, right? It's just they're now they're not v observation densities. Now they're v transition densities that show up in this kernel, right? But I haven't beat the curse of dimensionality. I still have the same problem. I've just shifted it somewhere else, right? So just using a Gibbs sampler doesn't help, right? I mean, this is the issue. You can't expect magic in some sense, right, from this story. Is it okay so far? Yeah.
You're integrating over dx
Made a bit of prime. Sorry, I've messed up my. This should not be a prime. You're correct. Right? So I start an x prime, then I go one step forward, and then I wait with the new observation. So the prime shouldn't have been up there. That's good.
Yeah, so x prime is just the coordinate at the previous time over which you are simply integrating.
Yes.
And in that sense, just notational, it should be just pi and. Okay, yeah.
But remember, this is, I mean, if we write this out, this is an empirical measure of n particles. So if I write this out as an algorithm, what I would do is at time n minus 1, right, I have n samples, right, of the field. Let's call them xn minus 1, 1, until xn minus 1, big N, right? These are n samples, right? So this is in the previous time step. These are my n particles in the previous time step, right? So now to sample from this distribution, I have to compute weights for these objects, and the weights, for example, the weight of the ith particle that I get from here will actually be the product of all v and v of p xn minus 1 I, and the v coordinate, sorry, now I take the neighborhood of v coordinates over here, x, now I have to think for a moment. So now we take xn. What are my weights? So I know all of these, right? So I have to, right? So it's this. Right? I've frozen all of the spins in the next time step except for the v coordinates, right? So what I have to do, I have too many v's. I have too many v's. Let's make this a w. So I know all of these except for the v coordinate, which I'm integrating against, right? So what I need to do is I need to integrate, okay, so what I need to do is the following. Need to integrate this against gv, xv, ynv. This is a one-dimensional integral. Right? So I have to compute these weights, but this is a one-dimensional integral, right? And then what I will do is I will basically sample xv from, what am I doing? xv. So I do this. I need to, I don't have, I need two steps. I need two steps. Yeah.
You're putting both the steps together.
Yeah, I'm putting both the steps together.
You sample from data n,
Yes.
which is using the density
So I'm going to do it all. I'm going to do it all at once, actually. But I mean,
So this transition density
yes.
is basically for the given by f is encoded in.
Yes, yes, yes.
And that you need to apply to
Yes.
each of these points.
So that's over here, right?
Right.
This becomes a conditional property. I mean, conditions the conditional ones because somewhere x b minus b should come in the equation. That's fixed. But in the formula on the right hand side, I don't see x b minus b. You see this formula?
So the little x and x prime have all the b's.
Okay, okay. So x
It also has the b and the
So a better way to understand this formula is as follows. Let me write out this P as a product over all of them except for V. So this is the neighborhood of W. Times, now we get PV, x prime neighborhood of V, xv, g xv, ynv, dxv, and you normalize by the same thing, right? Or, okay, right? So I've split it up, right, because this is the only part that depends on xv, right? And everything here doesn't depend on xv, right? So if you view these particles, so now we're okay, right? So if this is an empirical measure of n particles, then first I have to attach to each of these particles a weight that's determined by this object. And this object I can compute because I've frozen, you see I've frozen all the states except for V, right? So this gives me a weight for each of these particles, right? And now with this weighted measure, right? Now with this weighted measure, I basically have to compute this conditional distribution. Okay, so I have to then take this weighted measure and use that as an input over here. But, right, so I will, yeah, but the point is that this is a one-dimensional integral. So that's something you should easily be able to do, to sample from, right? Directly, right? But the point is you still get these weights on your original particles, and these weights, they're dimension minus one of them, right? So you still get the curse of dimensionality showing up for exactly the same reason as you got it before, except now it's the transition mechanism that's causing it, right, rather than the observations, because the observations dropped out, right? But in principle, I can sample from this fairly easily. This is a one-dimensional integral, which is why Gibbs samplers are nice, because they allow you to compute one-dimensional integrals over and over again, rather than have to compute a huge integral. But I'm not solving the problem, because I have here this full product of transition densities, right? Am I making sense? So this would be what would happen if I tried to apply a Gibbs sampler blindly to the particle filter. Wouldn't help. But here is where we're going to do our localization. So the point is that, you see so let's clarify it.
Sample from P. So x is given.
Yes.
So x n minus 1 is given. I'm looking at, I mean, if I have particles.
Yes.
So I have basically x n minus 1.
Yes.
Many of them. So I fix it. So I'm looking at a density px x prime.
Right.
Right? So I have the first coordinate that's given to me, each of the coordinates, and I simply sample from px prime.
Okay.
And I get my next.
But then you cannot compute conditional distributions.
No, and then you weigh them. So you have.
By
suppose
what?
you start with-
By what? By what?
So suppose these are equal weight.
Because you see, I need to sample. This is a distribution in XV.
So if each of these has equal weight, you go from here to x n minus 1 I. Each one of them is from p x n minus 1 I x prime.
Okay.
And so it's like it is distributed.
No,
like this.
XNI, like this.
Sorry, yeah.
Sorry.
Yeah.
Yes?
And now these are all again equal weight.
Okay.
And now you weigh them by using this fashion. Isn't that? how you-
Can I do that? So,
That's how you usually do the particle filters, the usual.
but this one also depends on X prime. So you would need to keep that one in track as well.
Yeah, so you keep all of them. So this xi I here includes all the so all the coordinates.
I don't think it's going to give the same, it's not going to give the right measure.
I'm just thinking of this.
I may be wrong.
So if I write this, the special case of this, let's say
So what are the weights that you're using?
f of x
What are the weights you're using?
plus this. If it's like this, right? If this density is basically the density for this. I mean, this is the density of x n minus f x n minus 1.
Right?
And so if the usual particle filter would be
Yeah.
you apply this, you sample that, you add it to each particle, then.
But that's not the equation we have over here, right? Because these are weights,
No,
you see.
so this is exactly
Right.
that much.
Right.
You apply this density to each
Yes.
particle.
Yep. Now we weight it by everything.
The reweighing
Right.
is only using observation.
Right.
The reweighing is not using the dynamics.
Right.
Not using the Markov.
But here we're conditioning also on the x's. So we have to be careful. So we have to look at this expression very carefully to see how to interpret this expression. You cannot just do what you're saying, right? You cannot, because if I first sample and then I try to compute conditional distributions, I get trivialities out. Empirical measures have bad conditional distributions, right? So we have to look at this expression and make sure that what makes sense, right? So in this expression, the question is, can you do this in several stages? And so this is so here are weights, so now we can, but you see the problem is, so we compute a weight, so this is just a weight on this guy. Okay. So we can normalize this one, and then we have to weight again using x prime and x v. So I could do it in 3 stages, but I don't know whether it's desirable. What I could first do is, you see this guy, I know all of these x's because I've conditioned on them, right? So I could take each particle, weight it by this quantity, which is a known, if I know the particle, then I can compute this number, use these as the weights, and sample from that. Right? Now I have here a measure, this sampled measure, but now I have to compute this distribution, right? So now I have to sample, given those resampled weights, I would now have to sample from xv according to that distribution, right? And then I would have to now bring in the new observation, which is a one-dimensional observation, and resample again. That seems like a bad idea. It seems like you can much better just, because this is a one-dimensional integral, it's probably very easy to sample from it directly. But how exactly you sample from this is not really important for my purposes. But the key point is that initially you get, on the original particles, you get these weights, and these weights are going to go to 0 exponentially fast in the dimension. And so you still have the cursive dimensionality showing up in this problem. Okay. So all of these, except for the V term, are giving you a weight on the previous, right? These are the weights coming from conditioning in the next time step on the x's, right? And then given this weighted distribution, you would have to sample from this, yeah. So indeed what would happen is, yeah, so the algorithm would be something like this. If you start, so you start with particles, x1 to xn. This is in the previous time step, right? And now what you're going to do is each of them is going to get a weight. And the weight is going to be the product of W in V except for V of PW xn minus 1 I NW XW. And these XWs are exactly the ones over here that I have frozen, right? And divided by the normalization, right? So now I have these weights. So now I'm going to resample particles from this measure, right? So I'm going to resample, right? So I'm going to get x1n to, not quite, let's put the tildes over them, right? Now given these particles, I can sample from this distribution, right? So now what I can do is I can now draw basically xnw but I'm now not, you see, now I'm not sampling the whole process, I'm just sampling the v coordinate here. So now I'm going to sample x n v, right? Sorry, x n I v is going to be sampled from basically PV of x n tilde I n v dot, right? Yeah, you know what I mean, right? And then I have to add the weight of one observation, right? So this would be the procedure, basically, right? But now I have to do this over and over again, because to run a Gibbs sampler, I have to do this over and over again, right? I have to do this, so now I update the v coordinate. The next I'm going to update the next coordinate, and the next coordinate, and the next coordinate, right? So these are not really the samples of times n minus 1 and n. At each time, I have to do this for as many rounds as I want to run the Gibbs sampler. So the theory is going to, okay, so in the end, when you run the theoretical analysis on the ultimate algorithm that we're looking at, which is one that's localized, you see that you don't need to run the Gibbs, at least theoretically, the Gibbs sampler, you don't need to run it for many rounds, because the error, the bias you get from making the localization, you need about as many rounds of the Gibbs sampler as the radius in which you're localizing, because that's the level at which the two errors balance out. So typically when you localize, it will have to be something like the log of the sample size. So this is going to be a very small number, 3, 4, right? So you probably only need like 3 or 4 rounds of Gibbs sampler to reach the, right? There's no point in going all the way to the limit in the Gibbs sampler, because at some point you're sampling from something that is already biased, right? So there's no point in running the Gibbs sampler for longer than you need to reduce the error of the Gibbs sampler to below the bias of what you're sampling from, right? So you will not need to run it for very long. So are we on the same page? So this is just to update, all of this is just to update one spin, right? And now you need to do this again and again and again, right? Repeatedly for each spin, basically. It looks much worse than it is. I mean, this is something you can implement easily. I think it's not really a big deal, right? It's just, I mean, the expressions get long, and then you need to sit down and you need to work on it.
Practice both these weights, generate with right? Fix some coordinates.
So they will be terrible because you have a product here of the size of the dimension.
Yeah.
So that. Yeah, so the curse of dimensionality is just as bad here as it was in the original model, right? So this doesn't solve the curse of dimensionality. But this shows us, okay, but now we're going to localize. So now that we're going to localize at the level of the conditional distribution. So to localize, what we're going to say is that, so now we're going to localize, but what we're going to use in localization, that the conditional distribution, so the decay of correlations, the notion of decay of correlations we're going to use is that the conditional distribution under the filter of a point given the rest doesn't depend too much on points that are far away, right? This is the notion we're going to use. And if that's true, then this should be approximately equal to the filter at the previous time step of xv as in A, but where we only condition now not on everything except for v, but just on x's in some R neighborhood of v, where nRV, this is the set of w's such that the distance between v and w is lesser or equal, right? So you see what we do is rather than conditioning the point on everything else, we just fix a circle around, right? So we have the point v, and we draw some ball of radius r around it, right? And we only compute the conditional distribution of this point given the other states inside this ball. Right? And this is where the decay of correlations comes in. So if you have decay of correlations of the filter, which we would need to prove, etc., but if you have it, then this should be approximately equal to this because the distant states don't affect the distribution of the state phi, right? But if you look at this object over here is actually the same formula, except now you have here the product, not over all of the other states, but you just get the product over these states in the R neighborhood of V. And the same in the normalization. So now, you see, we can stuff these guys into our Gibbs sampler. So now we've localized. The localization has just removed a whole bunch of this p's in the product, right? And now we can do exactly the same thing, except now when we compute these weights, we just use the transitions in some neighborhood of V, right? So by doing this, but you see now for each V, I've drawn a ball around V. That was in the previous algorithm, I had these boxes, and even if the V was all the way in the corner of a box, I didn't use really a neighborhood of V. I used sort of everything to one side. But here I update each site individually, and each time I update a site, I've sort of cut off a ball really centered at that site, right? But I've done it at the level of the conditional distributions, right? So this is where the localization comes in. The localization, so this, I didn't start from a bootstrap particle filter. I started from a different type of particle filter, a Gibbs sampling particle filter. But the Gibbs sampling particle filter doesn't help the cursor dimensionality. But the Gibbs sampling particle filter is easier to localize, right? So this is the idea, yeah. Yes?
So this would work, you would just go up and down your line.
Yes.
And you pick one, you condition on the ball around it, you swap it around, and then you pick another point on the line. Okay.
And you just keep doing this. And you have to do it a few times. So you have to pick each point a few times, but not all that many, probably. Right? So sort of the guidance is that typically these neighborhoods are going to be pretty small.
No, I mean, you can just, no, you don't need to pick all of them. You just need to do some kind of sampling on it. When you could cycle through, or you could do some kind of
So
sampling in a sense.
don't you actually need to go through the whole?
Yes. You need to do all of them a few times, right?
But I mean,
Yeah.
you could need to sample it.
Yes.
I mean, if one gets
But how you pick them?
Yeah.
No, if one gets missed, then that site is not updated, right? So typically what you can either round robin through them somehow, right? Or you can pick randomly in each iteration, but you need to do it enough times that the whole sample is type over.
on average.
Yeah, exactly.
You can't miss some sites and still.
But it would have to have very small probability, right? Yeah. But probably round robin, we analyze a round robin method. The round robin method is easier to analyze, yeah.
So this SN,
Yes.
really a few rounds of this.
Yes, so this SN, I'm abusing notation because before I said SN was sample IID from this measure, but I'm not doing, I'm not even doing that here, right? I'm now doing this SN truncated R, but this is really not SN as I had before. This is a Gibbs sampler. Yeah, so this SN is a few rounds of
This.
this, yes, and yeah,
But that few rounds
yes.
depends on the how many will depend on the size of the.
How many rounds or how long it will take?
How many rounds?
No, how many rounds is not going to depend on the size of V. So typically, and so you also have to worry about the truncation.
Yes.
So the truncation is typically usually the number of rounds should be of the same order as the truncation, according to the theory. And the truncation should be of order, it depends, but it's logarithmic in the sample size or worse. And this alpha is the actual dimension of your graph V. So this is not the cardinality of V. This is if you're, so Z, it would be D is 1, and Z2, not Z2, but the box, right, would be D is 2, etc. Right? This has to do with how many neighbors. This is really this has to do with how many neighbors each point has. Right? So typically the truncation has to be very, very small compared to the number of samples. So for realistic numbers of samples, you're not going to have the truncation size is going to be small, 2, 3, 4, something like this, right? And then you're going to do like 2, 3, 4 rounds of the Gibbs sampler, roughly speaking, right? So it's fairly, but it does not depend, nothing depends anymore on the number of sites you originally had, except each round, of course, you have to go through all the sites. But you're not going to get around that. I mean, even to read one particle into memory takes proportional to the number of sites time. I mean, the computational complexity of this algorithm can never be lower than linear in the dimension, right? Because even to write one particle takes linear in the dimension time, right? So the fact that you have to loop through the sites, right? So of course that will take the dimension time, but there's no, but that's just to compute one round of the Gibbs sampler. But the other algorithm that I have, even a normal particle filter would take that much time. Yeah. So, right. But other than that, so the dimension shows up in the sort of trivially in the complexity of the algorithm, but no more than that, right? So you see, this is why I didn't want to do it during the lecture. It becomes a bit of a mess, but I mean, we should talk about it as long until we get it straight. But this is the idea.
So the error that's introduced in that step then is linear in the size of v times exponential in the size of nv.
No, the error does not depend on the size of v.
It's linear because you're doing it that many times. Oh, sorry, no, so the error will depend on r. Yeah. E to the power of the cardinality of that set.
E to the power of minus lambda r is the difference between these two probabilities.
So the local error should be, this is not proved, but we believe it's true. The local error should be something like e to the minus lambda r. This comes from the truncation by this approximation, right? Plus e to the gamma times the size of nRV divided by square root n. Lambda and gamma, lambda is 1 over the correlation length of the field, and gamma is just some constant that depends on, basically depends on how spread out G and P are. But, you know.
So when you're talking about the blocks, there you said that the block size has to be chosen judiciously, optimally, because one
Right.
of that error was going up, the other was going down.
So that's what I write. So that's what I'm writing over here.
Same R will
So you see, if I'm in one spatial dimension, then a neighborhood is just an interval. So the size of the neighborhood is linear in R, right? So I have here e to the minus lambda r, and then here I have e to the gamma r, right? So to make those two of equal size, you have to choose r of order log n, right? Because there's an n down here, right? But if I'm in dimension 2, then nRV has r squared, right? So here I have e to the minus lambda r, but I have here e to the gamma r squared. So then I get square root log n should be more or less the, you know, up to some log n correction factor should be the right scaling, you see. So it's fairly slow, you see. So I mean, if you're in one spatial dimension, you get a polynomial error in the sample size. But if you are in higher spatial dimensions, you even get something slightly worse than polynomial in the sample size. But I assure you, it will beat, hands down, anything you do with a particle filter in high dimension. I mean, yeah, no matter what you do, it's going to beat the particle filter in high dimension. Often these types of methods work a lot better than you would think, right? This is theory, but you see in real life there are two things. This is the approximation error between the filter, between the algorithm and the filter itself, right? It doesn't say anything about how well this thing does in actually tracking the underlying state. It could be that the true filter does a bad job at tracking the underlying state, right? But often these things tend to work well, much better in practice than you think, because this is an algorithm that's designed to approximate the true filter, but actually it does a really good job anyway at tracking the underlying system, right? You could say the ensemble common filter doesn't approximate the real filter at all, but it still does a very good job in many systems, right? Much better than you would expect. If you try to prove an error bound between the ensemble common filter and the true filter, the error bound doesn't even go to 0, right? But the ensemble common filter still does very well, right? So that seems like a contradiction, but it's not. It's just, you know. So these types of methods will probably work much better in practice than the theory predicts, but at least the theory predicts a dimension-free error, right? And that's the key point in this sense. Now, as all things, these algorithms can be tuned. You can do importance sampling. I mean, you know, the models can be more complicated. This is just a, you know, idea.
E to the power minus lambda, I think works very well if you are, yeah, actually I can see that for Gaussian and variables it will all work. If etas and size are all Gaussian, but if they are not sub-Gaussian or anything of that sort, then
Sorry, say this again. What is sub-Gaussian?
the density being sub-Gaussian, it is not e to the power minus 6. Right?
Well, I mean, to run our theory, we need all these things to be in compact sets. Okay, because we need local mixing assumptions. And I mean, the assumptions we need to prove anything here are very strong. I mean, so for Gaussian systems, it has nothing to do with the tails. It has to do with the mixing. So the tails are not really relevant here. Yeah. Heavy tails are probably going to be better, actually.
The correlation lengths of the Gaussian random fields. So if you have a Gaussian random field with a nice correlation structure, typically
Right.
symmetric entropy that comes into
No, but you see, if you have a Gaussian random field, you start with the covariance, right? And then you get the random field from that. But so this, what I'm drawing here, is if you started with a covariance that decays exponentially, you would already have this, right? The point is that if you have these models, we don't start with a covariance. We start with a Markov chain, and we have to prove that the outcoming field has this type, right? You know, in the Gaussian case, you start with that in some sense, but here we have to prove that it's...
That's why I said that if I start with Gaussian, I see it.
Right.
But if
Yeah.
something else, and
But this is fairly, I mean, this is standard behavior in just for the same reason that Markov chains tend to converge exponentially to the invariant measure. For example, in a finite state space, right? You know, if they converge, they converge exponentially. And of course, there are examples of Markov chains that don't converge exponentially, but Markov chains tend to converge exponentially. Random fields tend to have exponential decay of correlation. If you don't, you just get something else over here, right? I mean, you could get a polynomial in R if you had a random field that decays polynomially, but you know. But that's the, our theory would definitely not capture that situation. No, but I don't want to give any misconception. The theory requires very strong assumption. We don't have the tools to study these things in a very, you know, in a very sharp way. But the whole point of this algorithm is that, you know, just to emphasize, the whole point of this algorithm is that in each state, we sample based on the neighborhood that's centered around that state, rather than a box where this thing can become asymmetric. Right? And in this formulation, with this Gibbs sampler, it's sort of clear how to do the localization. Right? Whereas if you switch the sampling in the C like you do in the bootstrap particle filter, it's not clear how to do the localization. We just don't know how to do it. Right? But here it's clear. And the inspiration for this, I mean, so the nice thing about doing the theory for the other filter, the one with the blocks, is that when we did the theory for the one with the blocks, which we could prove completely, the notion of decay of correlations that we needed was actually this notion. This approximation is actually what we needed to prove, even in the block case, in order to prove the block case. So once we had this, it sort of became clear that these conditional distributions are the natural objects to look at, and then we tried to exploit those actually to design the filter. So this was a sort of feedback from the, you know, we started with a sort of stupid algorithm, we did the theory, and then we used the theory as an inspiration to develop this algorithm. But like most theorists' algorithms, first of all, I've never programmed this. So Patrick has done some experiments on a very simple system and said it worked great. But you know, so I have some plots which are quite impressive. But actually, on simple systems, the block algorithm that I showed with the independent blocks works fantastically. It really is. If you run this, for example, so what we did, we ran on a common filter, just a linear system and a high-dimensional common filter. If you have a high-dimensional common filter, if you run a particle filter on a high-dimensional linear system, you can compute a common filter exactly, right? It's not so high-dimensional I have to go to ensemble common filter. I just really certainly take much longer.
yeah, there I have.
Yeah. But the point is, it's probably not a very, okay, I mean, no, I'm not claiming
It works very well.
for a very stupid system. I mean, you know, I think
But you also said that because the block. see,
our system was not a good model for anything
the problem
physical.
is that along the boundaries,
Yeah.
you have inconsistencies.
Right.
So, but the boundary, you also said that the measure of the particles on the boundaries is sort of going to be negligible as B becomes very large.
Okay, but listen, you don't have to take everything I say completely seriously.
Of course.
Okay. So on the one hand, I said I cheated, right? Because I said, okay, I have these independent blocks, and as these blocks get larger and larger, so it doesn't work on the boundaries. Theoretically, in practice, it seems to not be so bad in simple models. But I believe that this will not be good in physical models, because the models we're using are, you know, just a linear system with an almost diagonal, you know, with a tridiagonal A and a pretty large driving noise B, right? So you know, the real systems don't look like this, right? So, so I said that as the blocks get larger, so it doesn't work on the boundaries, but as the blocks get larger, the fraction of points on the boundary is negligible. But I also said that I have to choose the block size to tune it correctly out of order log of the number of particles. So in practice, the block size is not going to be more than 3 or 4. So, you know, you can't have it both ways, right? So in practice, that intuition that I had that you have very few points on the boundaries only sets in when the number of particles is prohibitively large, right? So the luck is that in certain cases, it seems that even this stupid block algorithm, okay, one thing I can tell you for sure, in any system, in data assimilation, any other system, the block algorithm is going to, for sure, I guarantee you, outperform the particle filter. The particle in high dimension, if you go to dimension, you know, 1,000 or something like this, the particle filter is completely useless. But the block algorithm will give you something reasonable. But I don't think the block algorithm is a good thing for physical systems because you get these artificial discontinuities on the boundaries, and it's going to just mess up your, it's going to mess up your physics, yeah.
For a very small system, it's very clear that the boundaries are going to
Yeah.
completely
Yeah,
they have a very large system.
yeah.
Makes sense to
So I think, you know, the block algorithm might be more useful for other applications. What?
have a very smooth
You introduce one back point in the model, and you create this, say, waves or something like that.
This is the thing, because things can propagate,
It's not that
you know.
having the boundaries being, so say, ratio 0, is still is bad.
Yeah, I don't think it will work for real
Introduce
systems.
a
I've seen the, yeah.
jump over a single line,
Outcome,
and
yeah.
you're already.
Yeah, so I mean, I'm not making any claims. I mean, that was an algorithm that we could analyze. But I think that algorithm might be more useful for, not for data assimilation applications, but for things like multi-target tracking or some, you know, other problems of filters that are still high dimensional where people, you know, need other algorithms. It would be a better algorithm than data assimilation problems have their own unique difficulties, you know.
If you have genuinely just ODs, very large.
Yeah. But this might work. I'm going to come to you. I just want to finish the, yeah. But you see, I think the nice thing about this approximation is it doesn't create any discontinuities, right? Because really what we're doing in this approximation is we're right? What we're saying is that the conditional distribution of each point given the rest only has a small. So what we're basically saying in some sense is that if you look at this thing as a random field, it's close to a Markov random field. But that's not such an unreasonable thing, right? A Markov random fields can have a very large correlation length, for example, right? So we're using the fact that the random field is close to a Markov random field, but it's sort of seamless, it's somehow continuous. So this process does not introduce any discontinuities. So I think that something like this has a much higher chance of being able to work in a complex model than this stupid algorithm with the blocks. But the stupid algorithm with the blocks has two advantages. First of all, it's very cheap to implement. Actually, it's much, much cheaper to implement than a particle filter because it can be parallelized like crazy. Like when you have these blocks, you can run each block on its own processor. It's wonderfully parallelizable, which an ordinary particle filter is not, right? So the block particle filter is very cheap, and we can analyze it theoretically. Whereas this, we're struggling, but I think there's, you know, we'll get there eventually. Yeah, so you had a question. The tail behavior of the random variables. You mean the tails of these distributions? So in the theory, you're talking about the theory, right? In the theory, we were assuming that all of these random variables are in compact spaces. So there are no tails. I mean, you know, the theory is hard enough in that, that setting, right? So in practice, heavy tails will probably actually make life easier. Yes, typically heavy tails make particle filters work better. So it's typically easier if the P's have heavy tails and the G's have light tails. The particle filters work very well because they create a lot of diversity somehow. But okay. So if you're in a situation where P is heavy-tailed and G is light-tailed, then the estimates become much sharper in the theory particle filters. So Dan, for example, has a paper where he does that. So, you know, it's very artificial in the sense that this never happens in real life. So what he would have to have is that the signal has a noise which is like exponential, and the observations would have to be Gaussian for that to work, right? This is not really a situation that happens in real life, right? Typically, they would both be Gaussian or something, right? But if you have such a setting where you artificially make this very heavy-tailed, that makes the theory a lot easier because it looks like a compact space. But we work, everything is compact. I mean, we assume very strong assumptions to make this work. I'm not claiming that it's realistic. I haven't thought about it. I mean, what is continuous setup? I mean, in your applications, you have a grid, right? So, of course, in the continuous setup, it's not realistic to assume these noises are independent, right? Because you should have some sort of smoothness also in the noise. So then you have to have, now you no longer have products over here. But you should be able to deal also still with some form of conditional distributions, but you know, in order to really make sense of that, you'd have to impose some model that makes sense. You have to look carefully. I mean, I have not made any attempts at, you know, we can't analyze this, so, you know, we have not made any attempt at understanding that. But, you know, and then you could attempt, you know, if you had a grid, you could attempt to estimate the error between the grid and the, I mean, okay, but, yeah. Yes. And the thing itself, right? The two neighbors and the thing itself, right? Yeah. Even with the one-dimensional case with two neighbors, it's a very complicated problem. Understanding even just, forget about the filter, understanding the behavior of Markov chains. These are called interacting Markov chains, or cellular automata, probabilistic cellular automata. They have horrible, horrible dynamics. I mean, these are not simple systems, because everything is coupled, right? So at time n, if you look at the dependence at time n, it depends on 2 to the n, or it depends on 2 to the n states at time 0, right? So the complexity grows exponentially in time. But you're interested in things that are uniform in space. So you have to understand exactly all the different routes of how information can be forgotten in the system. Yeah. Yes.
If you look at an observation, it's basically an interactive particle system.
Right. Yeah. And these are already very complicated. You have phase transitions.
Think of this as a simple Waters modular,
Yeah.
very basic exclusion process.
Yeah.
That's what is happening.
So you got all the nastiness of statistical mechanics already comes into play. Phase transitions, the, you know, structure of the extremal measures. I mean, you know, these are very complicated systems, and we're throwing observations on top of them, right? So, but then we impose really, really strong assumptions to say anything. So, you know, I don't want to pretend again that this is. Don't take this for anything else than it is. It's an attempt to work in a setting that's simple enough to be able to do some meaningful theory, and have some connection to something that might be useful. But I'm not sure that this would be useful in this particular form even, but, you know, it shows you a way to localize particle filters that at least seems reasonable, right? And I don't know of any other proposal in some sense that makes sense, right, to localize particle filters. So, you know, so for example, Dan has this work in high dimension, but he's not computing the filter, he's smoothing x0. Which is a completely different problem. That's not a hard, you know, Markov chain Monte Carlo will be able to do that without the curse of dimensionality, right? So their methods might be much cheaper, but they're not filtering, right? They're smoothing the initial condition. But if you look at the filters themselves, I don't know of anybody who is localizing or doing, I mean, it's because we don't know how to do it. So it's just, this is one way to do it that seems to make sense. But we can already not analyze this, but you know, there would have to be a lot of methodological work, which is certainly not my area, which, you know, to go into this, to turn this from a bunch of equations into something that somebody could actually use. But nonetheless, you know, it is what it is. Right? So I have a car coming in 10 minutes, I think. Yes.